So my name is Klaus Bergloff. For you who I've not met, I recognize a lot of people, so that's nice. Yes, so machine learning, digital twins, and AI. That's a lot of talk about that right now, and I think we are applying it in a maybe different way from a lot of things that is talked about. So I will try to give you an introduction on what we do and what can be done with the help of machine learning. So let's see if I can get the change. Yes. So we'll discuss just very briefly go through background and a little bit about ClimaCheck, but then we've focused a little bit on the cases, experiences, and so on, and then how predictive maintenance machine learning will affect what we are doing and what the industry is doing. So, I mean, those that know what we are doing, they know that we measure performance in systems to make them more efficient and more reliable. And opposite to most people who thinks that the system works when they reach the right temperature, we know that that's not the case. There's a saving potential of 25% at least without replacing equipment. Systems are not operating as well as they can because of how business have been done in the industry for centuries. ClimaCheck, I started with this in the mid-80s when there was a heat pump boom in Sweden, and people buy heat pumps to save energy or actually to decrease the cost. So if you don't make the cost savings that you expect, you complain. And there can be many reasons for that, and some are related to inefficiency in the system. And of course, sometimes you have given the wrong information when you made the calculations. But there was a lot of focus on that during the heat pump boom in Sweden at that time. A lot of complaints and frustration between equipment owners, contractors, and manufacturers. So I got involved in that and figured that there would be possibilities to use the thermodynamics that I studied at the Royal Institute of Technology here. And it is. And I think that's well proven today. So we base everything we do on the method that was developed then. ClimaCheck was formed in 2004. There was equipment for performance monitoring on the market in the meantime. But 2004, there were suddenly laptops available in the market. So it was totally different from when we started. In 2007, we launched ClimaCheck Online. It's quite obvious that these systems will, in the future, be more and more handled with data collection to the cloud. It's so many benefits of collecting the data centrally. There will not be expertise in each machine room. The expertise will be concentrate the information in the cloud. So we have continuously worked with development with customers. We supply about 50 OEMs with equipment for their development test rigs and production test rigs, and also for prototype testing and aftermarket. We have OEMs now that are starting to supply their units with connection to ClimaCheck Online as standard. Of course, we work with a lot of equipment owners because they need to put a request on their suppliers of service. Otherwise, they will never get a different quality of services. And we have many partners in the industry, but it has been a challenge to interest the industry as long as the equipment owners do not make the request. We also work with research projects. We have worked a lot with RISE, that is a research institute of Sweden that they have a big sector for energy and heat pumps, and they have had a test laboratory and so on. So we worked, first time they evaluated the ClimaCheck method was in 1989. We also work with other universities and institutes around the world. Today we have more than 100 man years of engineering experience of troubleshooting optimization of this system. So we try to, of course, expand our network and of distributors and partners and customers, but we are selling globally, and we say that we are on all continents except for Antarctica. And we are, I think, recognized as world leader in what we do. The left-hand table is made by NREL, National Renewable Energy Laboratory. It's a part of Department of Energy in US. They evaluated all automated fault detection and diagnosis system available on the US market. And there was one system that reached level 3, and that was ClimaCheck. Level 3 means that you detect deviations on component level. And we are talking not about taking care of an alarm, we are talking about detecting when there are deviations. And ClimaCheck was the only system they could identify that could pinpoint problems to the compressor, condenser, evaporator, and so on. And you see that there are quite some much larger companies than ClimaCheck. It's Carrier, Trane, York, Honeywell, and Johnson Controls, for example, that are leaders in the BMS, but they do not have the resolution of the information that we have. The right-hand document is in International Energy Agency. They had a project to develop methods to long-term performance monitoring of ground source heat pump systems. Ground source heat pump system means also chillers in the International Energy Agency's vocabulary. So, and these guidelines, I can really recommend those. Even if you're not working with ground source heat pumps, they are generally valid. The system does not care if you have a cooling tower or if you have a ground source system. The methodology for measuring and analyzation, it would be the same. So we have, during the last couple of years, focused on how can we implement machine learning AI. And digital twins are extremely powerful. And the advantage we have is that when we look at component level, the thermodynamics give us exactly which parameter that will have an impact. So that means that the digital twins become very accurate. And we also, of course, have a structured database with data from thousands of sites, starting with data from 2007. So we cover virtually all air conditioning, refrigeration, heat pump applications that you can find on the market, from domestic systems up to district heating, cooling systems with 9 megawatt inputs per unit. So we have a lot of data, and it's proven extremely effective to use the AI tools available on this. The two master theses that we have done were done with the Royal Institute of Technology in Stockholm here, one with the Energy Department and one with the Information Technology Department. And we are also right now starting up a project together with RISE and Halmstad University, financed by the Swedish Energy Agency, to enhance and expand the use of AI, machine learning, for automated fault detection. So RISE is the project leader. If you would have any questions on this, I noticed that Metcal, who is the project leader, was also in the seminar. And you can say this will be the Swedish contribution to International Energy Agency Annex within digital services for heat pumps. So if any of you are involved in those projects or similar, that would be an interest to join that International Energy Agency Annex from your country, I mean, this will start soon. So then a little bit of experiences. This was a pilot that was done on 10 hospitals in USA, and they measured with ClimaCheck. They recommissioned the sites, and they proved huge savings, both on the energy side, but also on the maintenance side. And one of the interesting aspects was that when they had basically all sites needed to be recommissioned, there was different faults, different inefficiencies in virtually all the sites, which correspond to what we see basically everywhere. But they also focused on what happened after the recommissioning and the importance of monitoring the system continuously. So during the 6 months, they identified 24 issues that increased energy consumption with 10 to 15%, and sometimes much more. And the correction of these identified deviations corresponding to 130,000 dollars per year. So it is important to make the commissioning correctly, but then also to monitor it. And what is interesting when you look at the data they have published on that project, they covered 78 chillers when they had done the 25 hospitals. They identified 109 issues during 2019 and 2021. And you can see that there's a big variation of issues that they could pinpoint. So there is not one issue that is the vast majority of problems you find. The heat pumps and chillers and refrigeration systems, they are exposed to a lot of different parameters. So there's internal faults in the system, and there are things that are affected by the distribution systems on the cold or warm side. So it becomes quite a wide range. And of course, it has an extreme value to be able to pinpoint the problem. And to be able to pinpoint the problem, you need to have the resolution where you look at components inside the system. If you try to look at the outside of the system, it becomes extremely complex to go from that there is a deviation to knowing what it is. So they also looked at the savings on the maintenance. They reduced the maintenance cost over 5 years with 9%. That's quite a significant amount when you look at the fleet of chillers. Bernard, who is a leading engineering company in US, they service 1,600 hospitals in US. So they have now realized the potential of focusing on the chiller optimization in these. There's another project that was an early project, but it was awarded by the US organization ASHRAE in 2018 as energy saving project in the category of large system. This is Sands Casinos in Macau. There's 300 megawatt of cooling for 3 casinos. And they also achieved improvements in operation, both resulting in energy savings and in reduced maintenance costs. This is a case here in Sweden where it's a mall where they had chiller heat pumps with an aquifer taking the energy or dumping the energy into the ground and pumping water from some holes to other holes. And they reduced the energy consumption for those chillers to half without replacing the chillers. It was basically fixing a number of issues related to the aquifer and valves and pumps and so on, and mainly the control system. So before you had a control system controlling the chillers in a sadly enough very common way where the controls are way too aggressive for a big slow building. So the controller forced the chiller to run up and down continuously, which also at some loads caused the chiller to trip on oil issues. So they had to bring a technician out to recover the oil from the evaporator and restart the chiller. This was costly and frustrating, of course. After they had recommissioned the controls, you had a picture to the right. You can see that it was extremely much more well-balanced controls. And you always have both the building control and the chiller heat pump controls, and these need to be tuned, and they need to work at different loads and different climate conditions. If you don't check that, you can be fairly sure that they do not handle that automatically by themselves. Almost all systems need to be tuned with that into consideration. This is the same chiller, but they detected that the condenser were decreasing performance. So you can see that the condenser went down to 79% condenser efficiency, and then it was cleaned this fall, and it went back up to 84%. Totally, this was about 7% energy saving. But of course, there was no issues at this time. If they would have continued, they would have gotten issues when the condenser efficiency decreased further and they want high temperatures in the winter. They don't have a lot of margin on the condensers when they run them as heat pumps. You need to have your condenser efficient. We did a project for the German Energy Agency. They identified that there was no focus on energy efficiency in the refrigeration industry. Everybody expected the system to work if they kept the temperature as they were supposed to. So they said that they needed to push this development. So they issued a request for proposal for platform to benchmark systems. So we made a proposal based on the performance analytics, the performance of the components, unit, and then also the energy signatures, which are extremely useful. But we also added the normalization of the energy signatures. So you benchmark energy signature at different outdoor temperatures, but also on square meters or cubic meters in a cold store, or you can use for commercial refrigeration. There are some supermarket chains that identify the size, so to say, of the supermarket by corresponding meter of display case. So they have a factor for low temperature display cases to convert it to medium temp, and then cold rooms correspond to a certain number of meters of display case. So you factor in how much refrigeration there actually is in the system. As there will be, of course, some supermarket might have a much larger non-refrigeration area than others. So this project started in 2022, and we did together with Holger Kühl at Kühl Analyse, who is our distributor in Germany, and PropTech OS, which is a platform supplier for data handling, where they handle all possible data for properties, according to a standard that is called Real Estate Core, making it a standard platform for property owners covering the whole building. We only focus on the analytics of the refrigeration, air conditioning, and heat pump systems, but they have a powerful platform to collect and store data in general. And so we were awarded this, and the project just was finished mid this year. And so the platform is up running as a pilot with a number of sites. So it's proven to be working, and they are considering how they will work with it in the future. So the platform is using all the KPIs that we are using, and it gives all the data for early warning. But of course, today it was a the focus was the benchmarking factor. So it's not set up for automated fault detection at this time, but hopefully in the future they will add that to that platform and push it. Another aspect that comes up where we use the training of the energy signature. We used that in this project, which was a research project here in Sweden, together with the innovation agency Vinnova and a large contractor, and ICA, which is the biggest supermarket chain, and IKEA, looking at how do you reduce peak load during the time of 8 to 12 in the morning when the grid is really strained. So what we did is that we pre-charged the commercial refrigeration system, I mean the cold rooms and display cases, during the night. And then we reset the set points according to what the different display cases and rooms could handle, depending on what type of goods they had, how sensitive they were. You changed set point between day and between the low load or the hours when you wanted to shape the peak and other hours. So we could actually reduce the power consumption during the peak hours to half what it was before. And interesting enough, we didn't really calculate on the benefits of running the systems more at night with lower evaporation. But as the outdoor temperature is actually lower also, and it's more, the night temperature is more decrease more than what we decreased the evaporation set points. So we actually ended up with having significantly better COP of the system. So they saved 20% on the energy as well by running with a much more dynamic schedule. And of course, that was also savings on the cost of the maximum power they take, and also on energy. So it was very successful. There is a manual available in Swedish. We have made some summaries in English, but we might work more on that in the future. So, I mean, the ClimaCheck method, it's pure thermodynamics. This is a basic circuit, but as you know, there are hundreds of different configurations, but I think that we have run across most of them. We have hundreds of templates for anything from the most simple system like this to systems with booster systems, ejectors, ammonia systems with oil cooling, you name it. I think we can handle it today. But basically, all systems follow the same thermodynamics. And when we analyze, we get all the KPIs you need. This is the best service maintenance protocol that you can find in the world. And it's available 24/7 every minute. It's updated. And you can monitor any of these KPIs. I mean, there are, of course, the common ones like superheat, the subcool, approaches, delta T's, and so on. But as everything is changing all the time, the efficiencies are extremely useful. And the visualization in the dashboard helps a lot when you explain things, even for people who do not maybe understand all the technicalities. So it's a really powerful as it is. Then I mentioned the energy signatures, as the refrigeration air conditioning systems are affected both that the load is very often following the outdoor temperature, but also the performance is following the outdoor conditions in most sites. So you typically have a quite good correlation between outdoor temperature and energy consumption. This is one of the challenges why it's so difficult to prove if a change of system was beneficial or not. People try to compare March last year with March this year or last year with this year, but as the years are not the same, it's really dangerous to make a comparison based on calendar time. But if you look at the statistics at the given outdoor temperature, and you take into consideration if it's opening time of the store or office hours or whatever, you have different operating characteristics over different hours of the day. But if you take that into account, you get an energy signature that is really defining your energy consumption at every outdoor temperature. And this was then what we did with the German Energy Agency, was that we also took into consideration per square meter or per cubic meter or whatever normalization factor you want to use, which of course makes it quite powerful to use the train data to compare different sites. Because even if there are different locations, they will all have an overlap of temperatures. So you can start benchmarking your sites and train your energy signatures for the different sites. And then this is just an example of what we see in, I would say, the majority of sites. There is a lot of control issues. So in this case, this is a CO2 booster system with heat recovery, and it's equipped with variable speed drives and several compressors and so on. And then you see at night, when the load is lower, you see that the control cannot handle the situation. The gray here is the power, and there are several compressors starting and stopping, and this system don't need to do that. It has variable speed compressors. It can tune to virtually any capacity, and it should never be possible to start a compressor 1 minute and stop it. And to start two compressors at the same time virtually, it's not beneficial. You can see how the evaporation swing because of that. And of course, this has impact on all the expansion valves. It has impact on the gas cooler fans and so on. So it's not the preferred operation. But of course, if you come here during the day, you would not see this. So you need to look at also when you're not there. This is another system, again with variable speed available, but it's running up and down until we complained when we saw this, tried to get attention to fix it, but there was no action taken until they had a couple of compressor failures. It would have been very cost effective to create the right-hand situation before. So there is a wide range of issues that are common. Then there are, of course, many others that are not as common but occur. So I'm not going to go through these in detail. You will have the presentation, and the list can be made longer. But then we come to, I mean, we have used for energy signatures, we have been training on each site since a long time. But now we are implementing machine learning in a much more, a much wider way, where we look at the data on component level and on unit level. So this is showing the data from a chiller with two parallel compressors, and the upper gathering of data, the cluster of data here, it's showing that the condenser efficiency at part load is better than at full load. Not surprising. And this data up here is heat pump operation, and this data down here is air conditioning operation. So this heat pump chiller is running in the summer for air conditioning and in the winter for as a heat pump. But what this shows us is that to use traditional warnings is fairly complicated. because we would need to use different different intervals that would be optimal for part load and full load and summer and winter, because the total variation in condenser efficiency is between 75 and 95%. The yellow value is what the digital twin trained on another system of the same design tell us that it should do. And the blue is what is measured at every point. So this, of course, tells us that the digital twin is replicating this system extremely well. So, of course, to look at deviation from the digital twin is extremely much more efficient from engineering time and accuracy point than trying to set intervals. So if we then look at this over time, we get a digital twin that is at each measuring point, every minute is telling us where we should be if we selected a system to train on that was working correctly. So, of course, this makes our life extremely much easier to detect deviations with much less work. And we don't need to train, we don't need to run a system for a year and then train on it. Because of if we have this type of compressor, it will behave the same way in every system you install that compressor. The condenser will behave the same if you expose it to the same conditions. So you can train on selected systems that you know are working well in your database, and then you can use those digital twins for a large number of systems. And this graphs show that these are two different systems, but you can see that the correlation is extremely good. So you can see that one system is roughly 1% lower than the other, but it's very systematic. So that is far within we don't want to find, or it's not important to find issues at 1% level. Today, the issues are found at 20-30% issues, level of deviation. So to be able to detect a couple of percent deviation is extremely much better than what is done today. This is an example looking at the subcool of two different systems, where the yellow is the train system. And you can see that the variations is maybe from 7 to almost 10 degrees. So 3-4 degrees is the normal variation depending on operating conditions. And you can see here that the measured system has a slightly higher charge than the system that the digital twin was trained on. So that wouldn't be so easy to define when you have normal variations between 7 and 9.5. And you see that the other one is between 7.5 and 10. So then you can easily conclude that the tested system, the blue, has a slightly higher charge than the train system. And of course, this is extremely useful when we look at indirect leak detection. In many systems, subcool is the best indicator on a leak. And of course, if you have 3-4 degrees normal variation, it's difficult to detect deviations of 1 to 2 degrees. That would be quite a significant change of refrigerant charge. But if you have a digital twin, it becomes very easy. And even if I used a yellow digital twin, I could just allow a slightly different thresholds for the blue, because I know it has a slightly higher here we have something that causes thousands of compressor failures in Europe every year. It's tandem compressors where there are two issues causing failures. One is when the check valve is leaking on one of the compressors, then the other compressor fail. Worst case, you replace that compressor that failed, but the problem was caused by the other compressor, so you fail the next one. There is also an issue on these systems. If the expansion the valve at low capacity do not completely register the correct value for superheat, you can get some liquid that is not registered by the expansion device. It's fed back to the compressor, and you get the same compressor failures on that. It can be immediately detected on compressor efficiency because of if you get liquid coming back in oil, excess oil circulation, or in liquid carryover from the evaporator, you get the compressor efficiency that goes way out of bounds, and that will cause failure if you don't address the issue fairly soon. It can run for months, but it will fail. This is another interesting comparison. We have trained the digital twin on a really high efficient chiller, and then we have used it on a site where actually these two chillers were quoted, and the blue was selected. And you can see here that the yellow would have performed extremely much better, actually using 50% less energy if you selected the yellow one. Of course, with price differences, it might make sense in some places to choose a lower chiller with lower efficiency, but it can be very costly, and you should know what you do. So showing how efficient the digital twin is to compare what would be the outcome of using different chillers. And today, the sensors are installed almost as standard. There might be one or two temperatures that are missing. Power might not be split as we would recommend. We want to have power per refrigerant circuit, but it's minimal cost. If you do it when you specify a system, I would say it's virtually zero cost to specify sensors to be what you need for a complete thermodynamic evaluation. But today we get more data, I think, from APIs where the data is collected by a third party and sent to our server. Also gateways. I mean, we supply a Modbus gateway that any BMS can write to. We also have customers using their own gateways. I mean, what we are really experts on is analyzing the data. We supply also standalone turnkey systems to collect all the data, but that we do to overcome the obstacles of customers having to put together their own data collection system. And we still supply those because of the cost and challenges with getting into old systems which might not be well documented. Even if the sensors are there, it can be difficult to get a hold of them. So I think that the increasing pressure on cost effectiveness and sustainability will change the industry, and AI, machine learning, will make it possible. Everybody's complaining globally, I think, about the lack of competent technicians. It will not be necessary to have all competence on site. You don't need to send people out to figure out what the problem is. The servers can tell almost exactly what it is, and you can send out the competent guy with the right tools to do the right measure, instead of sending somebody out that need to identify the problem, which is much more challenging than fixing the problem. And of course, this would be easy if systems were working at one condition and one load. More and more, we have more complex operation of systems. We want to move the energy from that place to that place, because we don't want to waste all the heating energy that we take from the food. And if we can sell it to the neighbor, that's much better, more sustainable, and more energy efficient. So our systems are becoming more complex, but that I would say is not the problem to handle if you do it in a structured way. Also, we are not talking about that there are millions of identical systems in identical installations. Any a little bit larger system will be customized or custom made for that specific application. The chiller can be the same, but the system is not the same. So it becomes complex to know what it should do if you don't have efficient tools, and it's complex to detect the deviations unless you have good tools. And of course, what we have collected a lot of experience. We do trainings saying that, if you have this symptom, check A, B, and C to know if it's this or that cause of it. Of course, all this will be built into the machine learning, so you get also the following up step. You get help with them, identifying if maybe you already have information to pinpoint the problem to only one specific cause, or there might be two, but you might need to check something to identify if it's one or two, is fault A or B. And of course, this automation is totally required to handle the hundreds of millions of systems in the world that need to be more efficient. And my conviction is that it's going to require AI, machine learning, and structured ways of dealing with it. And it will be servers taking 98% of the work and then helping the technicians on what they need to do. So that was the presentation. And I hope that there are some questions.
Yes, thank you very much, Claes, for the presentation. We have the first question from Miguel, and that is based on your experience, how efficient is a CO2 system in warmer places versus a traditional HFC system?
I would say that it's an extremely complex question, and I wouldn't want to give it an answer, yes or no on that. I mean, it is a challenge with CO2 if you have no use of heat recovery. If you just run it transcritical compared to conventional, I wouldn't know exactly if it's always is using more energy or not. But if you start reusing energy for heat recovery, of course, you can certainly see that there are systems that are more efficient. But I am not really, you need to be very cautious when you compare information from different sites, because it's very often apples and pears that are compared. CO2 benefits a lot from heat recovery if you can reuse the energy. But it is challenging at high pressure ratios without heat recovery to match. Transcritical is not the positive factor.
Thank you very much. Let's see, can raise your hand or write the question, and I will forward it to Claes if you. Yes, from Holger, he wonders if you could tell a bit more about the peak load project in Sweden, and if there was there all CO2 systems on the peak load?
Yes, it was not a big range of system. It was IKEA selected one and ICA selected one. ICA is the biggest supermarket chain in Sweden. They selected one system each for the test, and they were both CO2.
Yes,
Sweden has a cold climate and very harsh regulations, so there is a lot of pressure on the commercial refrigeration. So CO2 is used quite a bit here, and both these systems were CO2.
We get a little bit insight in the project in itself. I mean, the idea behind dynamic controls and controlling the system based on the peaks, that is not dependent on the CO2 systems, and we've tried that in different a lot of different sites, and so it's from a project perspective and control the peaks that we do with more than CO2 systems.
Yeah. I mean, I would say that almost all customers in Sweden now are that we work with, at least, which might not be representative, but I think that peak shaving is going to be. I mean, everybody realize how important it is going to be because of the tariffs are changing drastically between maybe 4 o'clock in the morning and 9 o'clock in the morning. You have very, very different pricing. So if you can move kilowatt hours to nighttime, it's extremely cost effective from cost perspective. And if you can avoid high power consumption, I mean, if the maximum power you take during the high load hours is low, you also get the benefits on your tariffs from peak power, so to say. So, and I think it's very straightforward, simple thinking on what. I mean, if we have an air conditioning system in the building, the traditional way have been to turn it on just before the office hours or something like that. That might not make sense when you have, I mean, a very different tariff. You might want to start a little bit early. I mean, we have all this with free cooling, of course, at night, and you have many aspects on it. But it's obvious that if you need to run your chiller, it might be very much more cost effective to run it a little bit extra before peak hours and then turn it down. You have many hours in a big complex. You have many hours before the customers start complaining if you run a little bit higher water temperatures in your system.
Perfect. Then we have a question from Benjamin regarding the digital twins. And it is what has to be done to configure the digital twin for commercial refrigeration plant in supermarkets?
To be honest, I think that there are some aspects that you don't need to do anything different from chillers and heat pumps. I have to admit that we kind of started with chillers and heat pumps because they are a little bit easier from this aspect that there are not so many versions of the designs. You can pick some more or less very common layouts and so on. But of course, when it comes to compressor efficiency, there would be no differences. And then if you take conventional racks with air-cooled condenser, there would be very limited differences between them and air-cooled chillers. There would be some, but generally it would be quite similar. So it is it's really high on our priority now to also look at the commercial refrigeration systems, and we have currently we are running where we tell the machine learning platform, we tell it to look at data from this site over this period, and then for training, and then we tell it to look at this for test. Then we are now in the beta testing of our next generation platform, and it will be released gradually during next year. And there we have it integrated. So we already have it in operation there. So we will have the digital twin running in parallel to the system. So that will, of course, make life much easier. But so it will gradually be implemented during next year. And the supermarket is certainly high on the agenda for next step. So I will start looking at that. We have a number of projects here in Sweden, which are just now starting. So that will come very soon. And I think that we have some German projects where we should also look at this, and some in Greek as well.
Thank you very much. And the next question, how many hours are needed to peak shaving and optimizing a supermarket with a CO2 system?
Again, I don't think CO2 or non-CO2 makes any difference from that perspective. I think that, of course, the first time you work with it, it's going to take you some hour to figure out what you need to do. But the guidelines we made, they list the steps. And as I said, we intend to translate that to English. We have just not had the time to do it. But basically, there are some groceries that are more sensitive than others. So you need to identify that you don't affect the groceries negatively. You need to stay within the allowed range of temperature. You don't want to dehumidify too much and so on. There are a number of aspects that you need to take into consideration, but these are basically the same for most. If we take stores, there would be some that are sensitive and some that are less sensitive. So then you basically look at what do you have, and you you look at the time lag you have in the system. You can see that when you do changes, when you do defrost and things like that, you can see how slow the system is to respond, and you can easily test it. So if you then you can then you see, you look also identify how big. I might have 100 kilowatt installed, but what is the normal demand of the system at this outdoor temperature? Which is easy to use the energy signature to see. And then you say, okay, I want to limit not too much, but I only allow 60% of the expected demand. So you get, so you can hold back the increase sufficiently. So I think that you need to build a little bit of experience, but then I think it's not very time consuming when you have it's not so difficult, but you need to have some experience. And of course, it depends on which control system you have. But I think that most control systems today, they could have time settings and change set points automatically. And of course, you also put in so that if a display case goes is coming to the limit you allow, then you have a fallback position where you would not allow it to go outside, where you would allow more capacity. So it is, it's a strategy that you need to set up, and then you need to program your controller for it. But it's not rocket science.
Okay, here's a question from Mr. Vasile or Mr. Kassian. Klaus, do you consider the pressure exchanger PXG1300 will make CO2 system more attractive for hot climate?
To be honest, I don't know what it is. Sorry to say. I would guess we measure on them, but we only have the flow chart, so I don't know what PXG 1300 is. Can you turn on your microphone and clarify which heat exchanger there is?
Hi, class.
Hello.
Hi to all. So it's a new discovering to increase the efficiency of the CO2 system, mainly in hot climate. So to recover the energy of the high pressure fluid with high pressure, to recover with this kind of system was presented in in this year at Chilventa, and in Belgium was already implemented this system. It's a variant for ejectors, but it's more safe and reliable in operation.
Okay.
It's coming from dissolved water plants.
Okay.
60% has recovering for the water preparation.
If they claim to improve the energy efficiency with 60%, I would not believe it. But
30%, no, 30% in the very hot climate. The efficiency increase for CO2 if when the outside temperature is higher. I want to answer for the worrying of the colleagues from hot climate, where the CO2 must work only in transcritical range.
Yep. I mean, you have a challenge, and I mean, you know, there are also combined systems with CO2, and then you use another refrigerant for high state. I mean, there are very many combinations on it. I mean, if you like, I mean, if it would be interesting if you send me an email.
I will send you. I will send you the presentation. I will send you.
That's always interesting. I mean, we have seen the ejectors. We have quite a few systems using the ejectors, which can improve efficiency quite a lot on some systems. But yeah, so there is a lot of devices, and then it's the more devices you have, the more important it is that you make sure that they actually do what you expect them to. It becomes more and more complex, which is a challenge, I would say.
Yes, I will put on this chat to see everybody.
Okay.
Perfect.
Okay, thank you. Nice to see you. So good
Nice
to
to
hear
see
you.
Perfect. We are we are on time or a bit over time, but if anyone have more questions, it's fine to take them, and you can always email us afterwards. We will send out the presentation and this both the PowerPoint and the presentation, and
If you have any questions that come up later, just let us know.